So the basis idea is the average expected. In the long run, that if we were to have the instance of our random variable occur over and over again, on average, what would be the numerical outcome that we would get on average? Now, we also refer to this as the mean, mu. So you might see me show you with the notation of mu. And the idea here is that is on average. And the difference here, we got to remember that random variables differ. Random variable mean differs from a simple average because the probabilities of each numerical outcome are not equally likely. Okay, they are not equally likely. So if you have a bunch of outcomes like 1, 2, 3, and 4, let's say, so, you know, i.e. if x, the outcomes were -1, what were the outcomes that I had from yesterday's notes? Can somebody remind me? -1, 2, it was -1, 2, 8, and 16. When calculating the mean, now the idea here is we know that the probabilities of these x's were 0.8, 0.15, 0.04, and 0.01. And so the idea here being that these probabilities were not equally likely. And of course, we made this look a little bit better by saying x, p of x, -1, 2, 8, 16, and we matched up the probabilities. Okay? So we have these probabilities. They're all matched and lined up. And the question is, what is the average? All right? The average is not -1 plus 2 plus 8 plus 16 divided by 4. This is not how we do it. All right? And as such, we typically call it expected value or the mean. We won't call it the average, but it's more of a, we also might refer to this, and if you might have seen this in a past course, a weighted average. It's like your grades, right? So if you had your different grades in your courses or what you did, and then each one was weighted differently, that's what's going on in here. And our formula says that the mu of x, the mean of a random variable, x, is equal to e of x expected value of random variable x. All right, so those are just the same things, but usually we'll just see e of x is equal to the sum of x sub I times p of x sub I. All right, now, typically we would also see from I equals 1 to n or something like that. But as I showed you yesterday, when we talk about the sum, this means it's like the outcome of 1 times the probability of that outcome, plus the second outcome times the probability of its outcome, plus ... times the last, plus the last outcome times the probability of that outcome. So you just multiply and add, multiply and add, multiply and add for all of them. That's what the formula means. Questions? I'll do the example with the previous problem. So let's do an example of this problem right here for expected value. So here's the example. Using the following probability model, calculate the expected value. And you'll be asked two types of questions in your homework. One will be just this question, find the expected value. And the other question might be to create the probability model. So you might have to, for the first problem, I give you the probability model. And the second two problems, you have to create the probability models, all right? So the probability model that we had from yesterday, x, p of x, -1, 0. Oh, that's 0. 2, 8, 16, 0.25, 0. Oh, what am I doing? These are my old numbers. I changed the numbers. 0.8, 0.15, 0.04, and 0.01. All right. So the question is, what is the expected value? That if I said, hey, come play this game, and this is a game, for example, and 80% of the time you lose $1, 15% of the time you win $2, 4% of the time you win $8, and 1% of the time you win $16. Does this sound like a good game to play? Yes or no? So I get a no. So, I mean, the answer here is it sounds like a good game. You're winning $2, $8, $16. But until we do the math, we don't know if this is a good game or not. And this is typically what happens like with carnival games or those games that you're playing. You know, you have these really, really big prizes. You have a small, medium, large, or, super gigantic jumbo prize and stuff like that. But the chances of winning those are so small that most of the time you play, you win nothing. And you lose your money that you paid in order to play the game. So with that, let's actually calculate that if we had infinite money, should we play this game? If we had infinite tries and we can keep playing this forever and ever and ever, what is the amount? If it's positive, and the concept here is, if it is a positive answer, then that means it's a game that you should play. Positive expected value, you should play. This is the problem that a lot of people have, though. If you lose and you lost $1 so many times, or sometimes these games have negative value. You go to a casino, you play one of those scratchers for the lotto cards, lotto tickets, lotto scratchers. All of those games have what we refer to as negative expected value. You are expected to lose. Now, it's very minimal. It's very small. On average, for every dollar you put in, you might lose like 5 cents. So the expected value would be like -0.05. Doesn't sound bad. And the chance to win $1 million. But they've done that, and that's basically they're playing the long run game. Well, somebody's going to win money, enough people are going to play where the amount of money ends up averaging out, and you just multiply. If you played 1 million people played your scratcher, and on a million people lose 5 cents on average, 1 million times 5 cents is $10,000. Basically, they just made $10,000 off of that. So those are the type of things. So let's find the expected value. So the expected value of this random variable, and we're just going to use the formula, expected value is equal to the sum of x, p of x. That's the formula. You don't have to write the i's, but this is what it's given. Well, we don't know if it's negative because we have to figure it out. It just depends on what the probabilities are. So we'll figure out what it is, and I'll redo the problem such that it would be a different one. So we would it's how the math works. So it's the first outcome. So what's the first outcome?
-1.
So it'll be -1, and I'm going to multiply that by its probability.
0.8.
Then I'm going to add the next outcome.
2 times 0.15.
2 times 0.015, good, plus, finish it off, you can do it.
8 times 0.04 plus 16 times 0.01.
And that's how you do it. And this calculates the expected value that if I play this game over and over and over and over and over and over, in the long run, this is what I'll get. And can anybody do that calculation for me? No. So here's the thing. Here's how I know if my answer is right or wrong. First and foremost, my answer has to be between I know for certain my answer is between what two numbers? My expected value must land between what? What is my answer going to have to be between? If I told you the worst you can do is lose $1, the best you can do is win $16, then the average will be somewhere what? Everyone? -1 and 16. Your answer has to be somewhere within the outcomes. So you know you've done your math incorrectly if your answer is not between -1 and 16. Because those are the outputs. We're saying, what is the average output? And the outputs, the outcome, sorry, I don't want to say output, outcome is -1 through 16. So my answer I know has to be between. Now it might be, this one's going to be close to being negative. Let me see here. Let me pause the screen real quick. I did the calculation with the calculator, and everybody should be able to do that. And everybody should be able to get -0.02. Any questions on how to type that into the calculator to get it? So once again, you just go on the calculator. Okay. Just to re-show it again, I had that -1 times 0.8 plus 2 times 0.15 plus 8 times 0.04 plus 16 times 0.01. And it gave me negative, oh wait a minute, why did I got a different answer now? Oh, I put 0.1, not 0.15. Sorry. Five. There we go. Gotta make sure you type in the numbers correctly. All right. So I got -0.02. So this game, so what that means is that there is a negative expected value. As such, this is a bad game to play since losing on average, even if it's 2 cents. And basically this is how casinos / lottery scratchers work. Most of it, and it's a little bit more extreme. There's bigger prizes. But the chance of losing, most all of them lose, and you might lose like 90% of the time that you're going to lose, and then you have the big rewards, and so they entice you with this. So there is one single outcome that had the highest. Now, if I were just to shift this just a little bit, and I shifted these probabilities just a little bit, I can easily make this have a positive expected value. For example, if I made the -1 outcome probability be 0.7, it probably would be enough to change the answer. And if I distribute that 0.7 to the other values, it would make the difference, and I would get a positive expected value. Now, once again, my answer has to be between -1 and 16. Those are the only outcomes possible. That's the range of my outcomes. Therefore, my expected value must be in between there. Okay. So the way the problems go, so the very first problem in your homework is going to be very straightforward. You don't have to create a probability model. It's already there for you. In the other problems, you're going to have to create one. And so the idea here is that, these games, so on your homework, the idea is about games where there will be an end. So it's like the typical is if blank, then when blank, if blank, then when blank, and then finally else, you lose. So, this is basically your first outcome. And so, this is your first outcome, this is your second outcome, and the third outcome is technically just going to be $0, because if you lose. And so that's pretty much the premise for the outcomes. And then these are some probabilities. So this is the probability of the first outcome, the probability of the second outcome, and therefore if you lose, it's going to be 1 minus p of x of 1 minus p of x of 2. So you would subtract because the rest has to happen. And these right here are going to be probability problems. It's not going to explicitly say the probability of this happening is 80%. It's not going to say that. It's going to give you some type of situation where you're going to win or you're going to lose, and then you have to calculate the probability. Do basically the first problem together. Okay, so in this example, this is from your homework. I'm going to start you off with this first problem. I'm not going to finish it for you. And so the game goes that you're going to roll a die. All right. If it comes up a 6, you win. And I'm not going to do the problem exactly. Actually, let me change the numbers here just to change the innocence. If it comes up a 1, all right, if you roll a 1, you win $50. Okay? And I'm going to change it slightly, but it's basically the same thing as example 4. If not, roll again. If second roll is then a 1, you win $20. If not, roll again. Now, the game, I think, on your homework problem is only 2 rolls, but I want to do it with 3 rolls. If the third roll is a 1, you win $5, else you lose. Now, sometimes the game will say something like you might have put money into the game. So the game might cost you money. For example, the game might cost you $5 to play. All right. So, so if the game costs you $5, then basically you have to subtract it from the winnings in terms of your profit. But I don't think none of the problems in your homework do something like this. All right. So if there is some type of issue, and let me just, the game costs $5 to play. All right. So you can roll the dice and win $50. That sounds great. And we're gonna sound like, is this a good game? All right. Now, this problem is slightly different than question 4, but it's also very similar to question 6, which is the other one, because it costs money to play. So I'm kind of combining the two. Okay. So question A, we're going to create a probability model. All right. We're talking about profit here. So X equals the profit, not the amount of money won in the game. We're talking about profit. Okay, so X represents profit. So what are my, if I win the $50, do I really win $50? Yes, no. If you paid $5 to play the game and then you say, hey, here's $50, you rolled a 1, did you win $50? Yes or no? No. You really won $45 because it's the 50 minus the 5. And if you won 20, you didn't really win 20, you really win 15. And if you won 5, you really didn't win 5, you won 0. And then if not, you lose the game. So we need to figure out, and this is the idea, is that we roll a 1. This is the idea where it's not a 1 and then a 1. This would be not a 1, not a 1, and then a 1. So what's the probability that I roll a 1? If it's a die, you should feel comfortable with this. What's the probability I roll a 1? If you roll a die, a fair 6-sided die that goes 1 through 6, what is the chance that when you roll that die, it comes up a 1? Work with me, class. I want to get through these problems.
0.25.
No. 1 out of 6. There is a 1/6 chance of rolling a 1. There is one outcome that has a 1, and there are 6 different total outcomes: a 1, a 2, a 3, a 4, and a 5. Okay, if we win the game stops. All right, that's the premise. So if I had won the game, but the game goes on if I did not roll a 1. So I have to find out all the possible outcomes. So the next outcome would be not a 1, and then I roll a 1. So what's the probability that I didn't roll a 1 and then I rolled a 1? Well, this is the probability of not rolling a 1. So what's the probability of not rolling a 1? I'm pretty much spoon feeding you these problems, these answers, class. Yeah, 5, 6 times the probability of rolling a 1. You didn't roll a 1. Now what's the probability that you roll a 1 on the second time? A dice does not remember. So each roll is independent of the next. So what's the chance that I roll a 1 on the second roll after not rolling a 1 on the first? 1/6, which is 5/36. Okay, now I don't roll a 1, and then I don't roll a 1, and then I roll a 1. So that's going to be what? Class? Yeah. I could tell I was writing out. 5, 6, I didn't roll a 1. 5, 6, I didn't roll a 1 on my second roll. 1, 6, I do it on the last roll, which gives me 25 over, what is, and this is typically why we don't do 3 rolls. The number comes out very weird. 6 times 6 times 6. 216. So 25 over 216. Okay. Now I need to figure out, so I know that, so what does the other one have to be? So the probability of, of everything else is technically not a 1 and not a 1 and not a 1. So if that's the outcome that will end the game. So my answer is technically 5, 6 times 5, 6 times 5, 6. But I could have also realized that this is really just 1 minus 1, 6 minus 5, 36 minus 25 out of 36. This could be done in either of these two ways. These are going to be the same value, which is pretty interesting, mathematically speaking. So if I go to my calculator, it'd be 1 minus parentheses 1/6 minus parentheses 5, 6 times 1/6 minus parentheses 5, 6 times 5, 6 times 5, 1/6. 1/6. And if I hit math, enter, it gives me 125 over 216. And as I said, I could have also figured out that this answer was going to be 5, 6 times 5, 6 times 5, 6. 125 over 216. So 2 ways to get that final outcome. All right, the easiest way I always think of it is you can do, if your mind, it's how you think about the probability of that last outcome occurring. That last outcome occurs only if I lost 3 times in a row. I lost the first 3 times, the game is over. So 125 times 216. And there's my probability model. B, calculate the expected value. Okay, so we're going to multiply each of these outcomes times its given probability. Once you've already done the probability model, this is easy. So the expected value of x is equal to what? What do I do? Calculating. I'm calculating. I don't want the answer. I take the outcome, which is, for the first outcome, which is? Anybody? I take the first outcome, which is?
45.
45. I'm not asking you to do any of the calculations. It's literally like, what's that first outcome? 45, and I multiply it by its probability. The probability of getting 45 is?
1/6.
1/6. I'm going to add to that 15 times 1 over 36. Oh, sorry, 5 over 36. And I add to that 0 times 25 over 216. That was it, right? 25 over, yeah. Plus -5, or you can think of it as -5, times 125 over 216. And if you're asking, well, I know 0 times 25 over 216 times 0 times 25 over 216 is 0. Do I need to include that? The answer is yes, you need to show your work. And it'll be very important for what I'm going to show you tomorrow in tomorrow's formula. You'll be doing the same thing. You'll even utilize the same probability models that you create from tonight's homework. So you'll use your answers that I end up giving you if you have troubles setting up the probability model. Of course, your expected value is going to be incorrect if your probability model is incorrect, but they're two different things. First, make sure, can you create a probability model and read the problem and understand what it's asking? And second, can you do that formula calculations? All right, so I'll go to my calculator. 45 times 1/6 plus 15 times 5 divided by 36 plus 0 times 25 over 2/16 plus parentheses -5, or if you want to write -5, it's perfectly fine. All right, it's going to come out the same way, times 125 divided by 2/16. And this gives me 6, and it's dollars, this is money, so I'm going to say $6.69. Question C. Should you play this game? Explain. Now remember, this is profit. So should you play this game? Yes or no? Got to be careful with your wording, and that it would not be accepted for credit. Yes. So the answer is yes, because the expected value is positive. Side note. If we didn't take into account the $5 cost, then my probability model would have been, I'm going to use y and the probability of y. My probability model would have been 50, 20, 5, 0, and I would have gotten the same probabilities. And the expected value, as it turns out, and it is kind of what you expected, the expected value would actually turn out to be $11.69. And in this case, the answer would be yes, because expected winnings greater than cost of $5 to play. It's just profit. So I want to note that if you do not take into account the $5, so sometimes this question talks to you about what is known as revenue, and this is profit. So if you're thinking about the profit, then you have to subtract the $5. How much would you win on average in this game? Well, it turns out that you would win on average $11.69. However, each time you play the game, it's going to cost you $5. So in the end, you're winning $6.69 on average. And this is a great game. I'd play this game every single chance I would have. Yes, I might lose. And yes, most likely, and actually this one is, I'm not going to even lose that likely. We could have switched the game. Typically this game gets switched. And they'll make the first time you'll lose. If you roll a 1, you lose. And then, you lose your money or something like that. So, or usually they redo the calculations. You'll see on the problem from your homework tonight, very similar to this problem. Problem 4 is very similar about rolling a die and you're just trying to get a 6. The second question is very similar, except for you're throwing darts. When you go to the carnivals, you've seen those people throw darts and they hit the balloon and you win. It's the same thing, but they say the probability of hitting the dart and they give it to you is 0.1. So it's almost the same thing. Instead of using the 1/6 as you'll use in this problem or in problem 4, you'll use 0.1 as the probability of winning on that first chance. And then of course, if you don't win on that first chance, then that means you've lost, and then you try again, and then you only have a certain amount of money to play. So in problem 6, the idea is the game costs $5 to play, but you only have $20. So if you lose your $20, you can't keep playing. So basically, these are, in this case, this would be a scenario of you only had $15. So this problem right here would be the scenario of you only have $15. So in this game, you can only try to win 3 times, and after you haven't won, then you lose everything. So you no longer win any money at all. So in problem 6, I want to note something. Every time in this game, you kept playing till you lost, the game was over. In the dart game, it's very similar, but every single time you play, you have to pay another $5. So let's say, for example, it was $50. Okay, and this goes to homework problem 4. The first time you win, you can only win $45. Okay, now let's say that on the second time you play the game, it's a little bit different. And I'm saying that ignore these numbers right here. You could still win $50, but you have to pay again. So how much money would you actually win in profit in that second game if you won $50? If you won on the second time you played the game?
And you have to pay 5 each time?
Yes.
Third? 20?
4. 40. It'd be 40. Because you would have paid $10 actually at that point in time in the game. So you would have paid $10 to play the game, and you would have won. You would have won $50. You're like, yay! You did it on the second try, but you paid 2 times. So your profit from the game is only $40 from winning on that second time. And then you play the game a third time, and if you were to win on the third try, you'd win the $50. But you paid $15 to play the game, so therefore your profit, your winnings would be $35. And so that's the premise for problem 6, is that although the winnings are the same, every time you play the game and every time you attempt, you have to pay an extra $5. So the first time you win, you don't actually win the $50, you really win $45 because you had to pay $5. The second time you actually don't win the $50 because you had to pay twice, so you really only won $40. That's the premise for question 6. That's what I have for you for today. I'll see you tomorrow. Have a good day.